Hello everybody. In this section, we're going to look at some more properties of definite integrals. Now, we've already seen a few of them. Now that we know that the fundamental theorem of calculus connects definite integrals with antiderivatives, we already know about the sum and difference rule, the constant multiple rule, right? Those adding or subtracting or having a constant multiple doesn't complicate your antiderivative, and therefore it doesn't complicate your definite integral. But there's some other cool properties that I want to talk about that come in handy in specific situations. The one we're going to start with, property number 1, is if you have the definite integral from a to b of some function f of x dx, then one property this has is if you pick a new x value, something different than a and b. Remember, a and b represent my bounds, and those are both x values. But if I pick a new x value, let's say c, I can split this up into two separate integrals, one going from a to c, and the other one going from c to b. And I can add those together. This might seem a little confusing, but let me draw you a picture to show kind of what's happening. If you have some function, and you're finding the integral from a to b, that means you're finding the area under the curve from a to b. All this property is saying is I can pick some value somewhere in the middle, and then split that up into two different areas. I can find the area from A to C, and then find the area from C to B, and add those areas together to get my total area. So that's all that this property tells us. And now that we understand that better, we might look at that and say, well, yeah, of course that makes sense. Why would that ever actually be helpful? And I'll show you an example. What if you have something like this, where you've got some function, and you want to find the area from A to B? Well, what do we notice? We notice that some of the area is going to be above the x-axis. Another piece of that area is going to be below the x-axis. This area right here is going to be counted as negative, and this area is going to be counted as positive. And so if I just do the integral from a to b of this function, it'll give me the net area, meaning it'll count the negative area as negative and the positive area as positive, and combine them together and give you kind of the balance. If there's more negative area, you'll end up with a negative value. If there's more positive area, you'll end up with a positive value. But what if I didn't want the net area or the balance of area? I want to just know what's my total area. What if I want this area to be counted as positive instead? Then what I can do is I can split this up using this point right here where it switches from positive to negative. And I can split this up into two different integrals. A to C. If I just think about this integral right here, what's going to be true about this area? It's going to be positive because all of the area is positive from A to C. And then I can look at that area from C to B. And this area we know will be negative. So if I want to make it positive, all I have to do is just change the sign. And now it'll count that area as positive instead of it counting as a negative value. That's one area where this property actually comes in handy and is helpful for us. The next property I want to talk about isn't quite as mathematical as the other ones. This one's more conceptual. So what this property states is if you have the definite integral of the difference between two functions, this actually represents the area between the functions for this interval a to b. This is, of course, assuming, right, we started with f of x, so we're assuming that f of x is bigger than g of x over this interval. So what do I mean by this? Well, let's draw another picture. If this is my bigger function f of x, and here's my lesser function g of x, notice I did draw some spots where g of x is bigger than f of x, but as long as it's true within the interval that we're talking about, a to b, then I can use this property. So if I have two functions, one is above the other one, and I take the definite integral between a and b, what this will give me is it'll give me the area between these two functions. And that's all this property really says. So you'll get a few examples on this in the homework for you to kind of try out. But something to keep in mind with these type of problems is sometimes it's tough to know which function is bigger than the other one. So what happens if you mess it up? What happens if you accidentally pick your smaller function to go on top? What if you accidentally write it with your smaller function first, subtracting your bigger function? Well, it turns out all that will happen is you'll get the same answer. Your answer will just be a negative instead of a positive. With these area between functions type of problems, we always want the answer to be positive. So if you do all the work and your answer ends up negative, you probably have the right number. All you have to do is just drop the negative. Just turn your answer to a positive and you've probably got the right answer. Okay, the last property that we're going to talk about deals with average value. So it turns out the average value of a function over an interval, a to b, can be calculated using a definite integral. So I can calculate it by just taking the integral of the function over the interval a to b and then multiplying by 1 over b minus a, or dividing by b minus a. So where does this come from? I use this word average, and you might be thinking, wait, I already know how to calculate average. To calculate average, you get your sum of all your values, and you divide by the number of values. Right? That's how you find values. You add them all up and divide by how many there are. This only works with a finite number of values, with a finite data set. But if I'm working with a function, a continuous function, I technically have an infinite number of values. How can I calculate average if I have an infinite number of data points? Well, let me draw a picture to make sense of what's actually going on here. So let's say I've got a function, and you want to find the average value of that function from a to b. What do we mean by average value? Well, we're talking about average y value. What's the average output value of this function in between this interval? Well, using an integral, using a definite integral, I can find the area of this function. And what I'm going to do is, let's take this weird area shape that we're given here and smush it into the shape of a rectangle. I'm going to smush this into the shape of a rectangle, keeping the bounds the same. So keeping it between a and b. So of course we'll need to smush this part down, and this part will probably come up. But I'm smushing it into the shape of a rectangle. By smushing into the shape of a rectangle, I now have one y value to worry about. Guess what that y value is? That y value is going to be my average function value. And therefore, because this area of the rectangle matches the area under the curve, I can figure out that y value just using my area formula for a rectangle. Base times height equals my area. What's my area? My area is the definite integral. The height is that average value. And the base is just this distance, which is just b minus a. That's where this formula comes from. The average value is just 1 over b minus a, because that's dividing this piece multiplied by your integral. So, using integrals, using area under the curve, we can calculate the average value of a function over a specific interval, as long as I have a function to work with. But those are our 3 properties that we're going to talk about today. In our examples video, we'll probably go through a problem of each type, just so you can see each of these in action. But go ahead and try the homework, and as you get stuck, go check out the examples video. Thanks.